Okay, I think it's four sharp. Recording started. Very good. Okay, we'll start. This is a great crowd. Please, I'll take the opportunity just to advertise. This series is it's a series. Please attend all the other talks as well. Yeah, that number, it's amazing. It's one of our biggest audiences. That's great. A warm welcome for our own Professor Ling, who's going to talk about phase transitions and systems of impurities and perfections. Sean has been here since the 90s, before many of you were born. That's what he asked me to say. and so we'll be delighted to see and hear about your recent work. But Sean, of course, has done a lot of seminal contributions in different fields: colloidal physics, condensed matter physics, nanopores. And so there's a bit more on the theoretical side of it, right? So
I'm going to give a survey.
Okay, excellent. So looking forward to that first. Thank you.
Okay, thank you very much, Matthias, for the invitation. Matthias said, he couldn't find anyone to speak for this week, and you need someone to speak for free. I said, sure. And my own students had asked me, what have you done to trick Brown University to keep you for such a long time? I should give a talk about what I did. Over the years, Alexander Kosterlitz was my first Ph.D. student. He is now a full professor at the Sloan Kettering Institute in New York. Sam Park is my second Ph.D. He's a senior scientist in Zoom, and they're all doing good things. One thing is for sure is everyone makes more than I do. So, you cannot do worse than me. Okay? So today I'm going to tell you about the problem that I'd be interested in is phase transition in a system with disorder. So this seminar series is called the Houghton seminar series. Many of you never saw Professor Anthony Houghton before. This is a picture of him. He and his wife generously donated to Brown University to sponsor this seminar series. In the past, we used to be really on a tight shoestring on who to invite. We couldn't pay for anyone from California for coming to that seminar in the past. Okay, so I should start with the question: the physics of phase transition. So we know that all solids melt. So the question is, what is a phase transition? To understand why they all must melt is, if you think about some energy scale versus temperature, thermal energy keeps going up with increasing temperature. And then the bonding energy is finite. For example, for ice is hydrogen bond. And then at some point in temperature, and we know what the temperature is for ice, right? And this morning was a few degrees above, right? We're somewhere here. Okay, so it will melt. Okay, so for more exotic matter like vortex lattice and the crystals, and then their interaction energy for quantum mechanical reasons, it has to go down with increasing temperature. And then when you meet this thermal energy line, and then it will cross, and then the thermal energy will down. It will also melt. So everything will melt. So the question is a phase transition. So why is this even a question? Okay, so because in one dimension there cannot be a phase transition. Why? Because if you think about it, I know there are physics 160 students here. We did a model of a ball connected by springs. Okay, so if you have a chain of a length x, you hold one end and you pull the other end by the amount of u, then the strain in the chain is u divided by x. So because this displacement is shared by every spring. So this is the strain. Strain times elastic constant is stress, and then stress times strain is energy per unit volume. That's in this deformation. Okay, so see u over x squared. So the energy cost to create such a deformation in one dimension is times the volume. Volume is just the length. You will get something that the energy cost that goes as 1 over x. And then at final temperature, and then the equipartition principle says the average of this elastic energy cost is half a kBt. And then you will find that then, on average, typically the displacement, the mean square displacement of the last ball will go linearly with x. So if you have a stick that's a spring that's long enough, and then this x will be infinity, so then this displacement will diverge. So in other words, if you hold this one-dimensional object, you don't know where the other end is. So this may sound a little strange, right? Because if you think about the stick here, from one end to the other, there are many atoms in between. If I move one end, the other end move the same amount. This is because it's three-dimensional. Okay, if it's one-dimensional, you hold this end, and the other end can be in infinity. Okay, so in one dimension there cannot be a phase transition. So this was known since the 30s. And if you do the same argument for 3 dimensions, you will find that this displacement goes as 1 over x. So when x goes to infinity, this is 0. But well, okay, in 3-dimensional solid, it does have thermal expansion due to nonlinearity in the system, but there's no divergent thermal fluctuations. Okay, if there were, then we will have trouble building a high-rise building, right? And we can't build a high-rise building because this thing goes to 0. Okay, so 3D melting is possible. Of course, we know that in England during this time of the year. In 2 dimensions, however, we'll do the same trick. You will find, okay, so this is elastic energy density times the volume. Volume in 2 dimensions is the area, x squared. So then when you do this, you find that there is no more dependence on x. Okay, so when you do the math properly, you find it depends on the length logarithmically. So this was known by Landau and Parels in the 40s. Whether there's a phase transition or not, this was debated for a long time, but finally a young postdoc at Birmingham, by Kosterlitz, who's sitting here, and David Thouless solved this problem. And then for 2D melting was refined by Halpern, Nelson, and Young. So it's called the KT and HY theory. Okay. So just a very quick one-slide introduction what KT theory is. KT theory basically says in 2 dimensions, if it's a superfluid, then at a low temperature, the energy cost to create a free vortex cost, the energy cost goes log of the system size. The thermodynamic, that's infinite, right? But if you create a pair, then that goes as costs log of the distance, so it's finite. If it only costs you a finite amount of energy, and then at finite temperature, this is going to happen. Okay, so you will have pairs, but they don't destroy the superfluidity in the system. With increasing temperature, you have more of this stuff, and then soon, then vortex and anti-vortex, they don't know who's pair. So they was started to essentially swap partners. And then if you zoom out a large length scale, you find the largest pair no longer feel each other. Okay, so why? Because the interaction between them has been screened by essentially the ions in between. So this is how ionic system become a plasma. So this KT transition is driven by the unbinding of topological defects. So obviously Nobel Prize work, it means hard work, right? You have to do lots of hard work to derive these 2 equations. And Professor Kosterlitz during the pandemic was very generous to wrote down all the mathematical details. Chao Shi here and Sijia Chen, who is now a PhD student at UMass, helped me. We typed Professor Kosterlitz' lecture into 3 big PDF files. You can find it in our website. Okay, how to derive this RG flow. Okay, so this was one big prediction is there's a universal jump out of the transition, and then so this solid line with the experimental data. There was no fitting parameter in this plot, so this is how good the theory prediction was. Okay, so when I came to Brown, my original plan was continuing that direction, because when I was a postdoc at NEC with Paul Chaikin and Shobha Bhattacharya, I found a peculiar phenomenon that is at f equal to 1. So in other words, you put one vortex in every hole in a square lattice, and then you still see a KT transition. How do I know? Because there's a jump from 3 to 1. So this is a IV curve. 1 means ohmic, okay, and 3 means it's a superconductor. Okay, so there's a real jump in the exponent, in this exponent. So this was predicted by the KT theory. But you're not supposed to see it at f equal to 1. You're supposed to see it at f equal to 0. Because why are you not supposed to see it at f equal to 1? Because every hole there's a vortex, okay? And then all the currents inside, they cancel each other out. So there's only one gigantic vortex of current on the edge outside. So this is supposed to break the vortex anti-vortex symmetry. So this is, you're not supposed to see it. But this is so clean. So I was obviously curious about this. So theory prediction that you're not supposed to have this. You're supposed to have ohmic response all the way. Because of f equal to 1, you always, the vortex to get excited, move a unit is finite energy cost. But I think this is still unsettled question, but I couldn't get the money to do it. And then, so the experiment I was involved in was, so this was recently decided by a Harvard quantum scientist that said, if you want to do long-range quantum computing, you have to do it this way. And I looked at the paper and said, the first author is still alive here. So the reason at that time, because there were only 3 places were interested in quantum computing. One is AEC, so that was AEC was paying me, and Shobha Bhattacharya. And then Fujitsu was also in Japan, and IBM. And then of course, so this is what I did. Okay, this is I can see there you can see there's a phase transition. So what happened was I could not get money to do it. So then I talked to the chair at that time, Professor Houghton. He said, "Well, you can do whatever you want. You don't have to. You tricked me by changing. So then, if I can do whatever I want." I said, what I really want to do is this problem, is the Imry-Ma problem. And at the time, I actually didn't know Tony did a lot of work in this area before. But anyway, so this is the famous Imry-Ma theorem. Unfortunately, both of them passed away. And then Jen, I think you know personally Shankar Ma. And I met Joe Imry once at AEC at Princeton, but unfortunately both of them passed away. So if there's a Nobel Prize on this problem, unfortunately there will be no one to collect. And then you guys will be free to try, okay? And hopefully by the end of the talk, you will realize this problem is not solved. Okay? So let me first state what the Imry-Ma theorem is. It's a very simple argument. Okay, imagine you have a ferromagnet, all spins pointing up. Now, in each site, you allow each spin to experience some random magnetic field pointing some random directions. So then each spin will pick up energy, either positive or negative. Then you know if you flip a coin with head and tail, equal probability of getting head and tail. If you flip n times, you will get a square root of n fluctuation, right? So you will get L to the D divided by 2. In the random energy gain. The cost to create a domain, of course, it would go as, we saw that before, it's 1 over L squared times L to the D dimension, right? So it's L to the D minus 2. So then if this guy is bigger than that guy, so which means this inequality, when this is satisfied, the system cannot have long-range order because the disorder wins. So which means we're living in a 1 to 3 dimension, right? So that means if the critical dimension is 4, then we live in a world that disorder always wins, right? So according to the Imry and Ma theorem, if it's a discrete symmetry, the spin can only have, but now the critical dimension is 2. Okay. So the first part of the Imry and Ma theorem actually was discovered by a Russian physicist 5 years earlier. I spoke to Professor Imry. He said that they did not see the Russian paper because of the Cold War. The Russian papers were not translated. Okay. So,
Sean, that was translated. I think the problem was different. That was a paper on superconductivity, and
okay.
it was infinitely far from superconductivity. The paper by Larkin is about superconducting processes. The
Okay.
paper by Imry about abstract models of statistical mechanics.
Okay. All right. Okay. So, thank you for the insight. That's Professor Feldman. He worked in Larkin's institute, right?
I knew him pretty well, yes.
Oh, you know him, okay. So this is what Larkin had discovered 5 years earlier. They were working on the following question. You have vortices pinned by random potential. So you have balls connected by springs. The interaction is the spring. The disorder is the values of this landscape. So you can work out the elastic energy cost. This is written in the density form. And then the gain from random potential. The cost goes like this. The gain from random potential looks like that. You add together, then you have a minimum. So what it means, the system has a ground state that's of a finite size. Okay, so then Larkin and his student Ovchinnikov wrote a very detailed theory explaining how the theory works. And they remember that displacement field for 1 dimension, when the average is over thermal average, here's the average over disorder. And then they got the same dependence that depends on R. If this thing depends on R, it means there's a loss of long-range order. Okay, this theory is useful because it now predicts a critical current that we experimentalists can measure goes as 1 over the square of the elastic constant. So the softening of the vortex lattice leads to stronger pinning. But the one thing they did not answer is the phase transition. So they were motivated. Of course, they didn't write that model out of vacuum. They tried to explain this phenomenon that was discovered before I was born. Okay, so I know I've been here before many of you were born. And so this problem was there before I was born. And then it was all forgotten. And then I accidentally discovered in 91 when I was your age. Okay. And then, so I'm going to declare before I retire that this problem is not solved. I'm going to hand the ball to you. You guys solve it. Okay. And now I will explain to you what the problem is. Okay. So if you take niobium, okay, so it's one of the elemental type 2 superconductors. If you take a wire and then you make it, grind it down into a wire, and then a strong wire has lots of code work in it, so the critical current is very high. But when you anneal it, make it very clean, and then the critical current drops by 2 orders of magnitude, and then peak shows up. If you take the same sample, measure resistance of a temperature in a fixed field, you see a minimum here. Okay, so you either call this a dip effect or peak effect, right? But in America, dip is a bad name, so everybody peak. So this is called a peak effect.
I'm gonna go with chips.
Okay, so
where is the actual DC?
Okay, so the TC in 0 for TC for niobium is 9.2. So this is in the field, in the magnetic field. So in the field, so there's the TC is suppressed, right? So somewhere when the superconductor goes normal, this happens. Okay, the question is a phase transition. Okay. So during that time, so when I was in graduate school, I read this paper with a lot of excitement, and one of them is Professor Bragg is sitting here. Okay, so this is the famous Houghton Condensed paper. Sootball, I believe, was a Ph.D. student, right? Bob?
What's up? I'm over here.
Bob.
Yeah, what about Subo?
Oh, he was a graduate student.
Yeah, he was telling me great.
Oh, good, okay. So they basically wrote down the following theory, which cannot be wrong. Let me explain to you why. Okay. Basically, what they said, well, if you look at the elastic energy, it goes down with increasing temperature, right? So, and there are quantum mechanical reason why this has to be the case. Okay. And the thermal energy goes up, and then when you equate it to, so this is called the Lindemann criteria. Okay. So this is when you don't have an exact theory on how the things falls apart. This gives you an order of magnitude estimate. So what this allows you to do is to give an estimate when this thermal displacement is big enough to make the lattice unstable. So there was a famous experiment was done by Bishop. Remember Bishop? It's the same Bishop Repi. Bishop Repi was done when Bishop was graduate student. This experiment was done when Bishop was a big shot in Bell Labs, and Peter Gamma, I believe, was his postdoc staff.
He was his staff.
Oh, staff. Okay. So they did this beautiful experiment. They took a silicon cantilever. Basically, it's a micro machine, a little device. It has a very high Q in vacuum. Okay. So they glue the crystal on it. Then they measure. It's like a tuning fork. They just measure the response of the tuning fork when you apply in a fixed field measure as a function of temperature. And then they see a big peak in the dissipation, and this, in the real part, they see the change in frequency. This right, but notice it's monotonic. Okay. So then they said, well, this has got to be the melting of the vortex lattice. So if you take this line, you fit it into the Houghton Condensed suitable paper, it really works. Okay. But then the question is, the people start saying, wait a second, in the Houghton Condensed suitable paper, there's no consideration for how the random pinning would do to the vortex lattice at all. They took a very brave step, saying, well, we just forget it. We ignore it, and then this is what's going to happen. Okay. Nevertheless, okay, so I didn't know that much as a graduate student, right? I took a crystal, so this is when I was a graduate student at University of Connecticut. By the way, for those graduate students think Bragg is not good enough for you, think about how I was thinking at that time in Connecticut. I almost transferred to Yale by making a mistake. Okay, but my professor convinced me to stay, and then a year later I did this work. Okay, and then okay, you can say, well, you didn't publish in PRL. Well, it was rejected by PRL. Why? Because everyone said, well, look at the field code, zero field code, the system becomes reversible here, and your effect happens somewhere there. Okay, apparently there's nothing there, no pinning there, and you have this big dip in the real part of the symptometry. So it took a long time. I couldn't win the battle. My thesis advisor was very helpful. He convinced this Navy Naval Research Lab organizer to invite me to a special conference and allow my work to be published there. And this is my written evidence. I actually was the one discovered. So if you work out a Larkin model, the critical current goes as 1/c, right? So when the vortex lattice goes soft, eventually this goes up. The question is the phase transition.
Sean?
Yes.
Did anybody measure heat capacity for that?
Okay. Yeah. Yes. The answer later. Yeah. You will see. I will show you something very soon. So then the question here is, if the system has random pinning or real materials do, and so according to Imry-Ma theorem, there is no long-range order. Can you still have a phase transition? So theorist gets very serious about this again. So there's three theorists recalculated this, assuming there's no topological defect. They found that displacement, rather than linear with L, it goes as log L. If it's log, remember in 2D, it's quasi-long range order, right? So they say, well, this 3D system is a Bragg glass. So if you go to Bragg diffraction, you should see Bragg peaks. But if you look closely, it's not a crystal, so it's a glass. So then, therefore, a real phase transition can take place. Okay. during that time, there's another Russian paper and considered a slightly different model. Okay, and then I was reading it the other day to check his RG equation to see how he got it. So Professor Dima Feldman is sitting here. So at the time, I think he was a postdoc at Weizmann Institute. And when he came to hear job interview, I was on sabbatical. I was so excited. So convinced him to come, but then he changed his research interest. Okay.
Sean, I was intimidated.
Okay. So speaking of thermodynamics, so I didn't give you this specific data, but if you look at the equilibrium magnetization, it turns out that when Walter Hardy's group in UPC made this YBC really clean, we got a sample, and we measured the magnetization jump happens right in the middle of the peak effect. So and then this was actually verified multiple times. Okay. So we needed a structure evidence. So we need to do this kind of experiment. You can do real time to monitor where the peak effect is and then look at the structure shape. So the experiment needs something big. Okay, so this is at the time 20 megawatt nuclear reactor right outside of Washington, D.C. I don't know if President Trump knows there's a nuclear facility near where he lives. You might want to shut it down. Okay, so so this is a NG3. This is a big vacuum tube. The detector is here, and our instrument is here. This is a human size. Okay, so the experiment is done here. The detector is there. Okay, so then we really zoom in, and we see the direct evidence for the phase transition. Okay, when you so when you know what you're looking for, and then life will become easier. And what happened was, so neutron scattering diffraction has existed way before us, and then seeing vortex light is way before us. No one bothered to check it, right? Because the Imry-Ma theorem says there's no phase transition. And then once we realize that there is a phase transition, we go look. Now everybody looks, everybody will find the phase transition. Okay, so this is the register. I didn't intentionally make us look thinner. Okay, so there's something wrong with it. And that's me. And this is the PhD student. And the Bridget McLean was the undergrad. Okay, so then after this experiment, and then people really questioned us, like, wow, in niobium, vortex lines are not supposed to melt because the vortex lines are rigid in the rod. If it's rigid rod, even if it is rigid rod, indeed you cannot have a phase transition because the energy cost to create an edge dislocation goes linear with the length. And then when you put in the thermodynamics, and then you see this is thermodynamic forbidden. So in order to have a phase transition, now then what happens is the line is not rigid rod, but it's wiggles. There are distortions along the z direction. And then so this is second generation of PhD student. Then he did this. And helped by Sam Park and Eva and Jeff was our host at NIST. And indeed, we see this giant hysteresis phase transition. Okay, so by that point, I thought that my legacy was safe. Okay, and then also I had another graduate student, Alexander's presented. So when Tony said you can do whatever you want, so I set aside $50,000 from my startup package to set up a colloid experiment, which I never did before. And then Alexander's did a really a good job, and to see the destruction of quasi. So this is quasi long range order with flat. Okay. Exponential decay is a loss of long range order. Then so this is for the young people here, young faculty member here. Okay, so I thought I can just I thought I'm done there. Okay, I should pick up something new to work on. So intrigued by how DNA polymerase. At that time, everybody wanted to do biophysics, right? So I said, well, actually, I do find it why DNA polymerase can replicate the human genome with such accuracy. So I set up with this project, and then, so this is a 15-year summary of the effort, okay? What it comes down to is this idea. I was really proud of this, okay? Because this idea came to me when I was on the plane after an NIH meeting from San Diego. I thought all I have to do is to take a single-strand DNA, pass through not 1 nanopore, but 2 nanopore in series. So then I have 2 resistors in series, right? So if I have a small oligonucleotide binding to it, if it's the correct binding, then this guy binding will be strong enough to survive this transit. But if it's weak, it will fall off, right? Then you can work out a kinetic theory. You find that you can improve accuracy by 100 million times. You probably don't believe it, and it's true, okay? But except, this is great, except it's not my idea. I reinvented, okay? I didn't know I reinvented somebody else's idea, okay? Professor Terry Hall came to me, I was telling him I was so excited, and he said, go read the Hopkins paper of 1975. I read it, and then we'll see his idea. So I find it very frustrating, okay? It's just, every time I thought I had a great idea, somebody had to say it before. So this is a full disclosure. At that time, with the former chair's approval, I went to China because NIH cut off my funding. So I went to China to do this, okay? And it got very close. This paper still hasn't been published, okay? It's a preprint. We managed to make this nanopore sandwich, and it's almost there. But then I was told I will be charged for treason if I don't come back. So the choice is between jail and the jail, because if I do go to China, I will be in jail for a different reason. So it's safer to come back to Providence. Okay, so I wrote it up during the pandemic, and then it got published, and I sent a copy to John Hopfield. And Hopfield said that he said it was a delightful surprise. Turned out someone, how to embed a fundamental kinetic proof. It will be wonderful to see this thing is actually working. Okay, so I tried to convince Matthias to do it. I cannot do it because I probably will be logging with the new director. He will definitely try to harass me. Okay. So during this time, and then my lunch buddy got a Nobel Prize in physics, and he invited me to Stockholm to attend his ceremony. Okay, that was a turning point in my thinking. And then the true moment was here when I walk out of the hotel. I tried to take a picture with Professor David Thouless, and then Deng Hongdeng walks from the behind. So now I'm surrounded by 3 Nobel laureates. I have no place to escape. Right?
Is Hopfield in front of you? This
Hopfield is on the front. So I tried to take a picture. Hopfield is not here. Oh,
I thought he's in front. It's not just.
No, Hopfield got the Nobel Prize this year, right? So last year. I actually wrote a nomination for him. Okay, so I think Mike was inviting me there with a real agenda states to remind me I did not finish what I come around to do, right? So Mike didn't say it. I think it's a general reminder is that my legacy is not secure, okay? Because if a problem is not understood, it will come back. Okay, so this is the latest from, I forgot it's Cornell or it's from Columbia. Columbia, okay. So they took a single layer now in the center line. You see, this is supposed to be clean limit, right? And then you see the peak effect there, okay. So Mark Lever in Europe, I think this is a Denmark neutron facility. They repeated what we did, and they zoomed in really deep in. Okay, did a more careful measurement. What they claim is, he said that the peak effect, however, is found to lie at a higher field to be in the region where thermal fluctuation of individual forces becomes significant. So what they're saying is, this is really the Houghton-Condensed suitable effect. In fact, so this is I stopped this neutron project because the DOE director tried to ask me to pressure my graduate student to accept jobs in places they don't want to go. So maybe I need to go back to neutron. I don't know. Okay. Maybe I can take over. Okay. So the peak of the peak effect is here. So the peak of the peak effect is here. The disordering happens there. The upper critical field is there. So somewhere in between is the peak effect. Okay. So there's the bottom line is there's no mechanism why the critical current goes up and why it comes down. Yeah. So basically it's a competition between thermal fluctuations and quantity disorder. So in order to come back, so after you have left a field for 15 years, you write a proposal to NSF, say, I want to get my grant renewed. You can imagine how brutal the review is going to be. And then the first round was no way, right? So then we have to, so I thought maybe I should take some time to get some data. So I convinced Brown University to let me to collaborate with Suzhou University. At the time, I managed to get Mike to visit and then allow us to pull off an experiment to show that the floating disorder can destroy long-range order in the system. Okay, so this basically allow us to, so when our second time when I submitted a proposal and NSF said yes.
So Sean, this is not frozen, a quench disorder, right?
This is floating disorder.
So, okay, so it's not really disorder in the sense of statistical mechanics, it's annealed, right?
Okay, so this is the question, right? So it turns out, this is what I believe, is there is no fundamental distinction between quantity disorder and floating disorder. It's the question of time scale. So what happens, right? Because if you think about quantity disorder in the vortex lattice, atoms are moving, it's just in the scale of vortex lattice, they don't.
No, the question is a question of thermal equilibrium. Quench disorder can be seen as a species of annealed disorder for a very unusual different choice of temperature for the system and disorder.
Yes.
And as long as the temperatures of annealed disorder and the system are different, the behavior is qualitatively the same as if it was quenched. But the whole point is that at the end of the day, the temperatures will be the same. Right. Then it changes.
Dima, this is a longer conversation. Okay. So all I want to say is we need to do an experiment on sharing this system to see the response beyond the domain size. So this is an experiment that Owen and Abdullah are trying hard. They convinced me they work really hard to try, right? Right? I don't know where Alexander said we work hard. He really meant it. But there's one time I was here at 3 o'clock a.m. and he was in the lab, okay, in the clean room. No, I don't want you to work out. Okay, so during this time, and we thought we should actually try some numerical work to start something simple. Okay, so the simplest model I thought was this 1 over r squared Ising model. Okay, so this model was solved using RG by Anderson and Yuval, and there was a long history of that. Okay, and then there's they used what's called the Poorman's scaling, which later is known as the renormalization group. Okay, it's basically tracing out this one spin or smallest domain wall pair in this calculation, and they can show there's a finite temperature phase transition. But if you add it to the random field, then what happens? So we did Monte Carlo. Is Jonah Ike, the former undergrad, who is now a PhD student at Columbia. So what they saw was and Owen and Abdullah. Okay, so the 3 of them, they did this Monte Carlo measuring magnetization as a function of temperature for the pure case. And then when they increase the disorder, so then looks like there's a reordering at a low temperature. Okay, so this I thought it was puzzling. Okay, so we did an exact calculation of so 2 to the n possible configurations. We find that there is a low energy gap in excitation. So when you use this all state to calculate the specific heat, there's a little bump at the low temperature. So there is a phase transition. Looks like there's a phase transition. And then I want to point out that the first person actually to point out there could be a survival of topological order was this paper by Tony Houghton, Ken Wei, and Sijin Yin. And then they said, however, it's not clear whether this argument, referring the Imry-Ma argument, okay, applies to the special case of D equal to 2, where phase transition is controlled by topological excitation. So I think I want to drive home a take-home message is, even though Professor Kosterlitz has received the Nobel Prize for this, I don't think we fully understand the destruction of topological order. There are more to be studied. I found that this, there might be another Nobel Prize, I don't know. Because every time I ask Mike always gives me the same answer. He doesn't know. Okay, so this is another paper by Tony Houghton with Jardine Goldschmidt. It's an adimorphism can show then that's why it exists at the intermediate. So basically they said there was a re-entrant phase transition. And this and Cardy and Osborne took it one step further, they draw a phase diagram. And then someone who are familiar with David Nelson even did more explicit to show the disorder versus temperature phase diagram looks like this. There's a solid phase, there's a hexatic phase, there's liquid, and at the low temperature, at 0 temperature, the Imry-Ma theorem always works. At finite temperature, there is a disorder to order transition. Yeah. So I actually know about David Nelson's work when I came to Brown, but I didn't pay too much attention because when I came here in 1995, a former Ph.D. student of Bert Halperin published a PRL on a numerical simulation to say that this dashed line is David Nelson's prediction, and the solid line is what they found in their numerical simulation. So I thought, I spoke to Mike from the Kosterlitz. He doesn't object to this. I was pretty distraught because I don't believe this is right.
Sure. Can I ask you,
because
what is
it violates the Imry-Ma theorem at the low
what's
temperature.
exactly the model? Where does disorder couple?
It coupled to random field
But no, disorder is random field, but it couples to what? Does
to
it
the
couple
position.
To the
This is a
position?
2D solid. This
The
is
position. I think a similar phase diagram has been rigorously established if disorder couples to the gradient of the phase, not the phase itself. Then I believe there is exact solution by now confirming the picture that looks like this paper.
Okay,
It's
so
not, but you're telling us the different
okay.
model.
Okay. Dima, I want to show you this.
Mhm.
When the full might of American power, Los Alamos, when they use their nuclear bomb simulation computers, turn into good use to study this effect. Okay, and I show you what they found. Okay, so this is the red line. What did they find? So the blue line was the vertical line. The green line is the Nelson line, and this is what they found. I believe if under President Trump more power is given to Los Alamos, more computing power is used for good use, we probably will see this red line goes all the way into the green line. I believe the green line is the correct one.
And so the disorder couples linearly to the other parameter, right? It's not
Yes.
to gradient.
Yes. So in this simulation, the Los Alamos also recovered peak effect. The peak effect happens here. Okay.
So do they claim that what was seen on the previous work is just a Griffith's phase?
What they saw was too small.
But that's an interesting thing because you would think that you need to go. So in principle, there is always a phase transition along these horizontal lines. You must have a Griffith's phase at the somewhere. But so the claim is.
So Dima, the biggest claim here, if you look at this phase diagram, what David Nelson says is the Imry and Ma theorem must be respected.
Mm-hmm.
Okay, and so both of these lines violated that.
Well, but Imry-Ma is not a theorem. That's the problem. It's extremely plausible argument, but no one has the slightest clue what happens when you move to a disorder control fixed point. That's the problem.
Okay.
It may be quite
Okay, we're gonna
long
know.
range order. It will look like actual order, for example.
I managed to convince Bob and Mike to teach me how to do renormalization group. So soon I can carry this conversation on you go.
But what if
Once
it's
I know all
what
the
if it's strong
approximations you guys did.
What is if it's a strong coupling fixed point? Then
Okay.
you're on your own.
Okay.
You can do whatever approximation you want, and you will get any of these phase diagrams.
You don't get any?
Yeah, you can get any of these depending on what
Okay,
uncontrollable approximation you make.
Okay, so this green line and this blue line was from the RG equation derived by David Nelson in 1982. To me, it sounds right. But it was cast out for 20-some years. Okay, so I didn't believe it until recently. Now I believe it, that we need to go back. And then this reinterest is a real effect. In fact, it was a thing in Bisco. So this is Zeldov's group in Israel. So this is where the magnetization jump happens. This is also magnetization jump happens, but this is also the peak effect happens. Okay, and then so this is Bisco is more anisotropic, and then so there is a re-entry effect. So I'm gonna so this talk mainly is for students. I wanted to discuss what our ongoing effort. We have a numerical studies of when the 1 of R square isomodel. Hope to finish this in the paper. So with Owen, Abdullah, Mike, and Bob, and then for my personal curiosity, I really want to understand if the simplest 1D isomodel with random field. Okay, so you're working with undergrad Rio Orengo and then a master student Yifei Zhang, and then experimental setup we're doing the sharing construct the colloidal cell to do 2D colloid crystal experiment, and then it turns out during the pandemic, Mike and I used to have coffee on Zoom, and we were wondering about what happens to a low angle brain boundary, whether you can think of it as a chain of edge dislocations. It turns out that David Nelson, same David Nelson, he wrote a paper already on this, and then they showed that there was a finite temperature phase transition. So this should be checked by experiment. So thanks to NSF for support. And the problem I really want to explore, if I had the money, unfortunately, when I go out to ask for donation, the university has a new policy that the money cannot come to my lab. I have to give it to the university. So I'm in a situation where there's no way out. So I don't know. So this is wishful thinking. So F equal to 1 problem in superconducting networks is not understood. I believe the destruction of topological order at F equal to 1 and the 0.61 that may be really fundamental way. Thank you.
Okay, thank you for a very nice talk, very entertaining, also very historical and cutting edge. Yeah, what questions do you have?
Maybe I offer not so much a question but the comments. My suggestion is that since you're doing experimental work and numerical work, I think you are safe, but you don't want to trust subtle theoretical organization group too much in this field. And the classical example, of course, is the Nobel Prize laureate you did not mention, Giorgio Parisi, who was one of several people who very beautifully showed that the normalization group just reduces a random field problem in d dimensions to a system without any disorder in d minus 2 dimensions.
But that result is wrong, right?
I believe it was first.
I think Bob even wrote about this.
Well, so that was this known as Parisi-Thouless reduction, even though I guess other people saw it before. But anyway, that was extremely beautiful, almost rigorous proof with supersymmetry. Experiment was firmly contradicting that from the very beginning. I read a lengthy paper by Parisi explaining that experimentalists are never able to reach true equilibrium, and so one should not look at what it And then, of course, at some point, Joe Imry simply proved a rigorous mathematical theorem. There is long-range order and three-dimensional random field Isaac model in contradiction to Parisi-Thouless reduction, and that's it. And that's where we are in this field. So I think you should be careful about it. diffusion group calculations, even if they are done by very famous physicists in this field. There are a lot of mess here.
No.
The problem is that there is actually a hidden infinite set of relevant operators. It's extremely hard to handle that. Even if you think that you find a weak coupling fixed point, the truth is that there are some ugly things which you just pretend are not there, and they can destroy the whole calculation.
Trust me, my trust in David Nelson is not blind trust. So yeah, I did find that his, for example, his first pass time calculation for nanopores turns out to be wrong because there was an exact solution for it, and the person solved it exactly. It was 100 years ago. His name was Erwin Schrödinger. So, and then it turns out that the exact solution contains a formula. You can just simply show. You can derive a rigorous DNA sequencing criteria, which is identical to Sanger's. But Sanger didn't know that, but still works. Okay.
Yeah, can you say something, quite generally, especially for this audience, about the relative importance of annealed and quenched disorder and thinking about the effects of disorder? I mean, your comment about it's just a matter of time scale, that's, that's something that would satisfy me as a theorist, but shouldn't satisfy you as an experimentalist.
Right. So I always thought window glass should be treated completely separately from a vortex glass. So that's my thinking for decades. Then I had a change of mind in that. I think that fundamentally this long wavelength rigidity part may be related. So remember in Kosterlitz-Thouless how the long wavelength rigidity came about is because of the topological order. It's protected by the topology of the system. So it's very possible there's phase transition in the window glass may not be equilibrium, but the appearance of long-range rigidity is the same. I don't know the answer to that. I think whoever has a clear answer is a Nobel laureate, I guarantee. Yeah, but that's indeed related to the Imry-Ma question as well. So, Professor Kosterlitz is retiring this year. And I plan to retire in 10 years. So soon, you guys need to step out to take over.
Okay, other questions?
All right, thank you very much.
I like it. It's like
Pretty good.
Never.
Well, actually, good progress. That's why I have to get the grant. I have to work on that over the summer.
So the way you so what you do is you can see you can drive the system by turbulence, going from one state to the other. Then the other is the equilibrium. You may not be true equilibrium, maybe even further, but it's more order or more disorder. This, whether it's equilibrium or not, this is like 100-year-old question. In chemistry, you guys deal with this.
Yeah. I would have pressed you on the window. That was a nice thought. I would have pressed you on the window glass case, right? So, so how even conceptually map that into an impurity or a problem with a disorder, in the sense that there's no underlying perfection about which you were perturbing, right? It's just it's topological disorder, and it's not so different locally from an order arrangement. Is disorder. So I don't know how you make these same kinds of arguments.
Yeah, so the question is the traditional way of treating the problem is we find its thermodynamic ground state, and then we find what's the low energy excitation, and then we build up the thermodynamics on top of that.
And if the low energy ground state is not ordered?
Even it's not ordered, right?
Yeah.
Right. So For example, you can say for point effect, right? You can the Franco's and all this work did on the point effect, and that's fine. But if you as soon as you deal with these locations in real solid, and then it becomes it becomes very difficult to address. Then it's essentially the same question we are addressing.
Yeah, it's just no easy way to think about
Right.
low temperature expansion would be something that takes some inputs.
Yes.
Right? There's no easy sets of dislocations. The material won't. There's no the material will fracture. It's not. It won't actually. It doesn't have the same kind of.
So the way I intended to probe this problem, I think after leaving the field for 15 years and come back, my head is clear, because then I have time to distill what's really important. And then I realized what's really important is long wavelength rigidity. So we should start from there and then probe the system and then look for the disorder, the structure disorder.
Okay. I mean, I understand what you're saying.
Yes.
Sorry, it was really nice stuff.
Thank you.
Quick question about the neutrons.
Yeah.
One of the thesis work was using X-ray optics to look at the quasi-long-range order in the liquid crystal.
Okay.
So 1982,
Cool.
34. Did the signature for quasi-long-range order show up in the neutron scatter? You know, the algebraic peaks.
Yes, you see that paper, but then it is.
Yeah. All right.
Yeah, you see that paper.
Look at
Yeah.
that. Okay.
Yeah, Imperial 2004 or something.
Beautiful.
Okay.
Thank you.
Thank you for coming.
Good work.
Oh, you have a question?
After you get oh no, just I think it's more of a I took like physics 160 with
Yes.
you, and you mentioned you were a big Real Madrid fan,
Yes.
and I'm from Madrid.
Oh, really?
Yeah, so I got it like when I was back home, I got you like a pin from Real Madrid.
Oh, wow.
Yeah.
Wow, thank you.
I heard it.
My son is also a real Madrid fan. I'm going to give him to him.
Yeah.
Oh, my God. Oh, thank you.
Yeah,
Oh,
I
Madrid
got it over the
just
winter, yeah.
just won a game yesterday. Oh,
Yeah, I saw.
beautiful.
Ooh, Barcelona.
Oh, well, thank you very much.
So, I think you're not gonna like what I say here,
Yes.
but I think I'm following slightly
Yes.
of what the issue here is
Yeah.
for the if you. Because I like that you look at different dimensions of this, you look at the two dimensions, and it's a logarithmic function,
Yes.
which is very important.
Yeah.
Because one of them is as you approach infinity, it goes to zero. The other one just diverges into nothingness. But in a two-dimensional scale, where you look at the tension of what you're stretching out, you see that you can actually map it on a logarithmic scale that will converge to something. And so what's interesting about what you said about how in between 1 and 3 there's a jump.
Mm-hmm.
So, and then also as you get very lower in temperature, you see more order,
Mm-hmm.
you see more disorder.
When there's quantity disorder.
Exactly. So you look at something similar to that, where you see disorder as you get very low and low and low in temperature, not in a solid state, in a gas state. You look at the Bose-Einstein condensate, which completely unrelated to what you just talked about, because you're looking at crystalline structures that eventually
No, Bose-Einstein condensate is referred to two-dimension with disorder.
you'll see the same thing.
Yeah.
Exactly.
Yeah.
But you can't. That's the world.
That's 2D XY model with disorder.
But the world we live in, right? What's the application of understanding if it's a phase transition or not in 2D? Where does that make sense in anything? I'm curious. Does it does it mean anything? If we were to find out that there is a transition, would that mean that there's like another state of matter that we're trying to figure out?
Yes.
That's exactly what it means.
Window glass, essentially.
So
Why window glass has long wavelength?
the idea is that two particles, you can think of them as charged together, positive and negative. As they separate in a disordered system, they start to lose effects on each other. I like how you think about it in a way of like just genuine, like an ocean. Like you have a bunch of water molecules here, and you have a magnet, and all the water molecules are magnets, or electrons and protons, they won't feel each other because they have effects on each other. But these guys are entangled, not actually entangled, but they are paired. How I would think about it instead is a graphical depiction of it as a concept of how you could. I mean, I also have no idea what I'm talking about, but how I would think about it is interference, like electric fields. In a way, I know this is way farther than I understand already. But if you think about two things that are disordered, no, if you think about a system that's disordered and you have two things that are supposed to be paired but slowly lose attraction to one another as more disorder comes in between them, then the only way to, it's like when we look at Newton's equation of gravity and we trust it, but we can't trust it because in reality, there's so much interference in between them that the force that they feel from each other is the force that it acts on the two paired things. I know that they're fundamentally paired because of quantum mechanics, right? Is that correct? They're like at the base level, like you look at their I don't know. I don't want to keep you too long, but I'm just thinking about some experiments that could be possible to figure out how to prove that as you get to n, because at n equals 1, what you were talking about, at n equals 2, I mean, d equals 2, which is talking about the dimensions, which is 2d, right? It doesn't make sense as you get smaller. There's a jump where it would make sense. Of course, you could isolate that and look at it at like just from the part where it jumps and from before and after. But the thing that makes it so, like, what you're studying is how you go from disorder to order, essentially, and in that state where you jump, there's a change in state of matter. Is that correct?
Yes. We think it is.
Yeah.
Well, according to David Nelson. So what happened was Professor David Nelson wrote this paper in 1982.
Okay.
And then in the 90s, basically, people said that was wrong because for this reason. I took the new people's word for it. Professor David Nelson never said either way. Okay.
And then versus this.
And then when the people who did really
experiment.
Numerical.
Oh, they found it plateau.
No, they found it going down.
Oh, they found the curve in between the two.
Yes. The plateau one was the one from Kentucky.
Oh, now that's definitely BS, right?
Well, that's what's.
So what does that plateau mean? What do they think it means?
There's a critical disorder strength beyond which the lattice becomes unstable, below which is stable.
Oh.
Basically, that was the same.
So they're saying that there's nothing special.
No, basically said that Imry-Ma theorem doesn't work for these two dimensions.
So they're saying it's incredibly special.
Yeah.
And this, the bell curve that looks like that, says it's not special.
No, the bell curve, the curve going down, that says at t equal to 0, Imry-Ma is correct.
Which means that
disorder wins.
Disorder
always wins.
So disorder beats order when we're talking about the ocean.
You're at a t equals 0. When you ignore thermal fluctuation entirely, just competition between random.
T as in what? Time or temperature? Temperature, of course. Sorry, what am I saying? So at temperature equals 0, which of course doesn't make any sense.
No. The argument. So the way we consider thermodynamics, right? F is equal to E minus T times S, right?
Yeah.
Okay. E is energy. It's entirely the interaction.
And you got entropy and enthalpy.
And then minus T times entropy. If T equals 0, then entropy terms goes away.
Yeah, which means
so
that you would just be
dominated by E.
Yeah.
Okay, E inside is just vortices interact with each other and then with random potential.
Which in general chemistry we think about it as bond energy, but in this it's different.
Okay, so in
this would, if it's not just bond energy, this would explain a different state of matter.
Yes.
I get it. Yeah. It's brilliant because
except that they're dead, so they're not here to collect the Nobel Prize.
I want to do it.
Yeah. Okay.
Can I work for you? How do I? Let me do it.
Okay.
How do I do this?
Okay, then I can give you Imry-Ma's paper, and then there are. Oh, you're a math guy, right?
Yeah.
There's some rigorous math you can read it, and then show me. You can choose through it. How about I give you a theory paper? You can derive the.
I learn things differently. I learn it by doing this, like.
No,
talking.
The math is.
I know that's different. I mean, I know.
Math is rigorous. You have to Your math is, you can't do a hand waving argument. You have to show.
Oh yeah, no, I could show the math.
Yeah.
But to
Okay.
learn the concepts, I can't read anything. I have to talk it and ask the right questions. But to find out if there's another state of matter that as D equals 2, right? You'd have to prove, because